Welcome back to the deep dive. Today is going to be a fun one because we are taking something that sounds terrifyingly mathematical, constraint satisfaction problems, or CSPs,
Right.
and realizing it's actually the hidden logic engine behind some of the most addictive puzzles we all play.
It is. And once you see the mechanics of CSPs, you never really look at a puzzle or even a logistics problem the same way again. It kind of changes how you see the world.
So to kick this off, I want to start with the thing that really hooked me. Sudoku.
The classic example.
Right.
Hmm.
Everyone knows the drill. You've got a grid, some numbers are filled in, and you have all these empty squares. To me, that's just, a way to kill time on a flight.
Mm-hmm.
But you're telling me that to a computer scientist, a Sudoku grid is something much more profound.
Oh, absolutely. To a computer scientist, a Sudoku grid is the perfect textbook example of a constraint satisfaction problem.
Right.
And it really represents a massive shift in how we think about artificial intelligence.
A shift away from what exactly?
Well, think about how we've talked about AI search in the past. Usually when an AI is trying to solve something like, say, navigating a maze, it treats the world as a black box.
A black box.
It doesn't really understand what's inside. It just tries a key. Does it open? No. Try the next key. It's searching blindly.
Okay, so it's just checking every possible state until it bumps into the goal.
Exactly. But with the CSP, we stop treating the state as a black box. We look inside. We use what's called a factored representation. We break the problem down into its pieces so we can actually reason about it.
Instead of just guessing.
Right.
Okay, so factored representation sounds like the technical term of the day. The notes break this down into this core triad: variables, domains, and constraints. I want to make sure I'm not overcomplicating this. How does that actually map onto a Sudoku board?
It's actually very intuitive. The variables, let's just call that X, are simply the things you need to set. In Sudoku, what are you trying to figure out?
The empty squares.
Bingo. The 81 squares on the grid, those are your variables.
Oh.
Now, for each of those squares, you have a limited menu of options you can pick from. That menu is the domain.
So in Sudoku, the domain is just the numbers 1 through 9.
Precisely. Variable is the square, domain is 1 through 9, and then finally you have the constraints.
The rules of the game.
Rules.
No two numbers the same in a row or a column or that little 3x3 box.
Right. And this is where the magic happens. In the old way of doing AI, that black box search, the computer doesn't really know those rules while it's searching.
It just checks at the end?
Yeah, it just fills in a bunch of numbers and then checks did I win.
Yeah.
But in a CSP, the AI uses those rules actively to prune the possibilities.
Prune, as in cutting down the bad choices.
Exactly. Imagine this massive tree of every possible filled-out Sudoku grid. It's enormous. Pruning means chopping off entire branches of that tree because, based on the rules, that they can't possibly work.
You eliminate massive chunks of wrong answers before you even try them.
You do, and it's exponentially more efficient. To illustrate this, let's maybe look at another classic example they use in the field: map coloring.
Right, the map of Australia.
Yep. You've got Western Australia, Northern Territory, Queensland, and so on. The goal is to color each region either red, green, or blue.
And the constraint is that no two neighboring regions can have the same color.
Simple enough. Now, I was looking at the math on this, and the difference is wild. If you just tried to brute force it, just testing every combination, you're looking at checking hundreds of potential assignments.
Just for a simple map like that?
Yes. But if you apply constraint propagation, which is basically just saying, hey, if South Australia is blue, I instantly know none of its neighbors can be blue.
Ah.
The possibilities just collapse. You go from, say, 243 options down to maybe 32. You've eliminated something like 87% of the work before you even started.
That's efficient. But I want to pause on the constraints part because in the real world, it's not always as simple as this can't be the same as that, is it? The logic gets messier.
It does. We categorize them to keep track. The simplest is a unary constraint. That just restricts a single variable.
The example in the notes was funny. South Australians won't tolerate the color green.
Right. It's a rule on just one node.
Yeah.
South Australia is not green. Then you have binary constraints, which is what we were just talking about.
Yeah.
SA can't be the same as WA.
And then there are the big ones, global constraints.
Or higher order constraints, yeah.
Huh.
This involves any number of variables. The most famous one you use in Sudoku constantly, is called all-diff.
All different.
Exactly. In a Sudoku row, you have 9 variables. The rule isn't just square 1 is not square 2. It's all 9 of these variables have to be distinct. That's a global constraint.
I also saw a mention of preference constraints. That felt a lot more like real life to me.
That is where the rubber meets the road. In the real world, it's not always about what's forbidden, it's about what's better. Think about scheduling classes at a university.
Okay.
Professor R can teach at 8 a.m. It's not forbidden, but he hates it. He prefers 2 p.m.
So the AI isn't just looking for any solution anymore.
Right, it turns the problem into a constraint optimization problem, or COP. You want the solution that violates the fewest preferences. You're optimizing for happiness or cost or whatever.
Okay, so we've got the board set up. We know the variables, domains, constraints. Now, how does the AI actually solve it? Because the notes make a huge distinction between searching and inference.
This is the critical concept. Searching is asking what if. It's guessing. Inference is asking what must be true. It's logic.
So we want to think before we act.
Exactly. We use constraint propagation. We want the constraints to ripple through the network and delete impossible values. There are two main levels here: node consistency and arc consistency.
Node consistency seems pretty straightforward. That's just checking those unary constraints, right? If South Australia hates green, you just cross green off its list.
Correct. That's the easy part.
Yeah.
But arc consistency, that is the bread and butter of these solvers. The algorithm's called EC3, but the concept is really just a domino effect.
Okay, walk me through that.
Okay, think of it as a chain reaction. Let's say you have a rule connecting variable x and variable y. Maybe the rule is that y has to be the square of x.
Okay, so if x is 2, y must be 4.
Right. Now let's say the domain for both of them is just the digits 0 through 9. That's all they're allowed to be.
Single digits only, got it.
So look at x. Can x be, say, 4?
Well, if x is 4, then y would have to be 16, but y can only be a single digit, so no, x can't be 4.
Boom. You just performed arc consistency. You didn't just check y. You realized that because y is limited, x is limited too. You inferred that.
So you can delete 4, 5, 6, 7, 8, and 9 from x's domain right away.
Immediately. And that's the domino effect, because now that you've shrunk x's domain, maybe that affects its other neighbor, z, and the logic just ripples through the whole graph.
This sounds exactly like what I do when I'm playing Sudoku and I find a naked triple.
It is. If you see 3 squares in a row that can only be, say, 1, 5, or 9, you know those numbers are locked in. You can cross 1, 5, and 9 off the rest of that row.
Right.
You feel clever doing it, but you're just running the AC3 algorithm in your head.
I feel slightly less magical now, but okay. So we use logic. We propagate constraints. But eventually, we hit a wall. We can't infer anything else. We have to guess.
And that brings us to the search phase. Usually, this is backtracking search. It's a depth-first search. You pick a variable, assign it a value, move on. If you hit a dead end, you backtrack.
But even here, we can be smarter. The notes mention 2 heuristics, or rules of thumb, for making these guesses, and they seem to be opposites, which kind of confuses me.
It is a bit of a paradox. You have to decide which variable to handle next, and then which value to assign to it.
Right.
For the variable, the rule is to fail first.
Wait, why would I want to fail?
Because if you're going to fail, you want to find out now, not 1,000 steps down the line. You pick the variable with the minimum remaining values, or MRV. If a map region only has one color left that works, you color it right now.
Because if I ignore it, I might accidentally steal its last possible color and create a conflict I won't see for ages.
Exactly. You tackle the tightest spot first. In Australia, you'd start with South Australia because it touches 5 other regions. It's the most constrained.
Okay, so fail first for the variable.
Yeah.
But for the value, the color itself, we do the opposite.
Yes. Once you've picked South Australia, you want to choose the color that is the least constraining value. You want the color that leaves the most options open for its neighbors.
So pick the troublemaker variable, but give it the friendliest value.
Perfectly put. Force the hard questions early, but answer them in the way that's most likely to let you keep going.
Now, even with all these smart strategies, you still get stuck sometimes. You hit a dead end and you have to backtrack. But the notes are pretty critical of standard backtracking. They call it chronological backtracking and basically say it's dumb.
It can be very dumb, yeah. Let's go back to the Australia map. Imagine you color South Australia, then New South Wales, and then finally you color Tasmania.
Tasmania, the island at the bottom.
Right. Now suppose you hit a snag that's caused by your choice for South Australia. Standard backtracking says undo the last thing you did. So it undoes Tasmania.
But Tasmania has nothing to do with South Australia. It's an island.
Exactly. Changing Tasmania won't fix the problem on the mainland, but the computer just backs up one step. It tries red for Tasmania, fails. Tries blue for Tasmania, fails. It wastes all this time fiddling with an irrelevant variable.
So how do we fix that?
We use intelligent backtracking, specifically something called backjumping.
Backjumping.
The AI keeps a conflict set, a list of which variables actually cause the problem. When it hits a wall, it doesn't just step back one step. It jumps all the way back to the most recent variable that is actually in the conflict set.
So it jumps over Tasmania and goes straight to the source of the problem.
Precisely. It saves a massive amount of time by ignoring its irrelevant mistakes.
That makes a ton of sense. But everything we've talked about so far assumes we're building a solution step by step. You start with an empty board, fill one square, then the next.
Instructive search, yes.
But what happens when the problem is just too big? Like, what if you have a million variables? Does that approach still work?
Usually, no. It's just too slow. For really massive problems, we switch strategies completely. We use local search.
And the idea here is you start with a wrong answer and just try to fix it.
That's it. You start with a complete, filled-out board that is full of errors. Then you just try to repair it.
The example given for this is the n-queens problem, putting queens on a chessboard so they don't attack each other.
Right. So imagine a board with a million squares and a million queens. You just plunk them all down randomly. It's a total disaster. They're all attacking each other.
So how do you fix a million queens?
You pick one queen at random, you look at her column, you count where the attacks are coming from, and you just move her to the square with the fewest attacks. This is the min conflicts heuristic.
So you're just putting out the biggest fire for that one single piece.
And you just repeat that.
Uh-huh.
And here's the absolutely shocking thing. This simple method can solve the million queens problem in an average of about 50 steps.
Wait, 50, 50, independent of the size.
Roughly, yes. It turns out that for many of these problems, the solutions are actually very densely distributed. If you just wiggle the pieces towards less conflict, you stumble upon a solution incredibly fast.
And this isn't just for, like, toy chess puzzles. The notes had a story about the Hubble Space Telescope that really stood out to me.
Oh, this is the killer app for local search.
I mean, scheduling a space telescope sounds like the ultimate nightmare. You've got targets that are only visible for minutes. You have power constraints, thermal constraints.
And astronomers all fighting for time. It's a massive, messy CSP.
NASA used to use that constructive step-by-step search. It took them 3 weeks to schedule 1 week of observations.
3 weeks? That's barely keeping up with real time.
Right. Then they switched to a min-conflicts local search algorithm. They started with a broken schedule and just wiggled the observations around to remove conflicts.
And the result?
They cut the scheduling time from 3 weeks down to 10 minutes. That is unbelievable. From 3 wins to 10 minutes just by changing the algorithm.
It really is. It shows the power of choosing the right approach for the problem.
We're coming towards the end, but we have to tackle this final section, which I found the most abstract, but also maybe the most powerful, the structure of problems.
Yes. This is where we zoom out. We stop looking at the individual variables and start looking at the shape of the problem itself.
The notes talk about tree structures as being sort of the holy grail here, but when I think of a tree, I think of branches. How does that apply to a data problem?
It's about the connections between the variables. In a tree structure, everything flows in one direction. There are no loops. A connects to B, B connects to C. But C never circles back and connects to A.
And why does that matter? Why are loops the enemy?
Because loops are what kill your efficiency. Loops are where you get stuck in a cycle of backtracking. You change A, it breaks B, you fix B, it breaks C, you fix C, and it breaks A again. You just go in circles.
And with a tree?
You just walk down the branch, you pick a value for A, then B that fits A, then C that fits B. You never have to look back. You can solve huge problems in linear time, basically, instantly, if you can prove they are trees.
And most real problems aren't trees, are they? The Australia map has loops all over it.
That's true.
WA touches NT, NT touches SA, SA touches WA. It's a triangle. That's a loop.
It is. But we can cheat. We can turn a graph into a tree using something called cutset conditioning.
Cutset. That sounds like surgery.
It kind of is. Imagine the graph is a tangled knot of string. If you could just snip 1 or 2 threads, the whole thing would unravel into a straight line.
So in the Australia map, what's the thread we snip?
South Australia. It's the hub connected to everything. If we just, for a moment, remove South Australia from the equation, the loop is broken. The rest of the map actually becomes a tree, or a forest of trees.
So how do you remove it? You still have to color it.
We cheat. We just assign a fixed value to it. We say, okay, let's pretend South Australia is blue. Now solve the rest of the map. And since the rest is a tree, that solution is instant.
And if that doesn't lead to a solution?
Then we try again. SA is red. Since the domain is small, we only have to solve the easy tree problem a few times. We turned one impossible graph problem into 3 very easy tree problems.
That is incredibly clever. You're finding the one keystone variable that holds all the complexity together and just fixing it in place.
Exactly. That small set of variables is called the cycle cut set. If you can find it, you can just crush the problem's complexity.
This has been a fascinating look under the hood. We started with a simple Sudoku, realized it's this language of variables and constraints. We learned how to use logic to prune the search space.
How to backtrack intelligently when we get stuck, and even how to just wiggle our way to a solution with local search when the problem is huge.
And that simply understanding the structure, finding the trees hidden in the graph, can turn an exponential nightmare into a linear breeze.
That's the whole journey.
Before we go, I want to leave you with one final thought from the source material that I'm still kind of wrapping my head around. Value symmetry.
Ah, yes. The symmetry of labels.
If you color the map of Australia and you find a solution with red, green, and blue to the computer, that's one unique solution. But if you just swapped every red crayon for a green crayon and every green for a red, isn't that mathematically the exact same map?
It is. It works the same way. The labels red and green are completely arbitrary. But a standard AI doesn't know that. It might waste time finding all the different color swap versions of the same core solution, thinking they are new discoveries.
So the provocative thought is, how much faster could our AI be if it simply realized that red is just a label? If we could teach it that the names don't matter, we could slash the search space by another huge factor.
That leads to a whole other deep dive on symmetry breaking. But essentially, yes. Sometimes the hardest constraint to satisfy is the one we impose on ourselves just by naming things.
Something to mull over the next time you're stuck on a Sudoku.
Thanks for listening to the deep dive. See you next time.